Alright, welcome back, generals, to another Let's Fix Generals 0 Hour to make the best game ever. Okay, so previous session we had implemented a bunch of stuff here. Base type and type info. I do wonder. This one here. If we look for a type info, like this one here, there's also type info and name here. Can we also maybe class type info, type info? Can we maybe can we maybe cast to this one here? Let me see. Call it type info. Type info. And then here we do a type info, type name. And then here we put this type name binary type info. Let's call this type info. There we go. Class type info. Okay, let's put it to class type info. And then we cast it to type info. dot data. This one we can also do const, and this as well. Const. Okay, so the class name is that thing. Oh no, it can't be const, class name. And then here we call this class name 2. And then we put an assert. Basically, we expect this symbol name here to match this one. Assert class name equals class name 2. Okay. What? Okay, let's put a breakpoint here. Wait, hold on, there's a mistake here. No, there's not. Actually, how about so this is type info. It's called type info B, and then we create a auto type info dot data and then we do type info this one and here we best pass type info. Oh. Hmm. I think what we do is like this, right? Okay, so class name is that, erase, overwritable. Can we maybe make it simpler here? I don't know. So type info is that. Okay. Class name 2 is overwritable. Assert this equals that. So I do wonder, is there any other information in this symbol? There's a section, type, description 80. Huh, what does that say, 80? 80. Size is 0. Description 80. Overwritable. Is this 80 maybe the size of the class? That would be interesting. What is that description? Let me see. If we go down here. I guess we can look a bit around. So for example, here we have base class, index. Description 80. Well, it's always 80. It's probably like flag. Description 80. Hmm. 80. Maybe we can ask ChatGPT. Maybe he has some ideas. Let's do let's just copy this, see if, oops. Let's just copy this here. I have a MachO symbol in leaf of type 1e. It has a description value of 0x8e. It has a description value of 80. What does that mean? What does that value refer to in this context? Flags and additional metadata are primarily used for special types of symbols such as RTTI. RTTI type info symbol from C++, type nsect next. The symbol is defined in a section. The symbol is externally visible. Description. What does it mean? Description field is a bit field containing various flags. Some important flags. nlist.h, we have that. Weak def. Weak def. It's a weak definition. Okay. Okay. Mm-hmm. Okay. Nlist. Mm-hmm. Mm-hmm. So here W. Hmm. I don't know how this is useful for us. But maybe I can put a note here. Type info. symbol.description. I don't know. If we don't use it, no. Okay, what next? I think this looks pretty decent. Now the question is, the next question, what do we do with the vtable? So for example, here we have vtable xfer. So there is a type info. There are two destructors. There's pure virtual. No. Okay, it seems to end on zeros. Yeah. Zeros. I'm a bit confused about the two destructors. How does that work? 1, 2, 3, 4, 5, 6. 6. Xfer map name. Xfer implementation. Okay, let's look at Xfer. We're already there. Xfer implementation 0. Okay. And here we have a pure virtuals. 1, 2, 3, 4, 5. Isn't this an error here? It should be pure virtual, no? I think so. This one here. It says file name, file name. But here it's pure virtual. What is this bullshit here? Class Xfer. Isn't this function supposed to be pure virtual? Okay, so the way I see it right now is that we look at those vtables, and if there is a pure virtual one, we need to look into a child class, to another vtable, and then see what that puts in there, what names. Yeah. So we have 1, 2, 3, 4, 5, 6. X for snapshot. X for snapshot. Yeah. Mm-hmm. 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 Okay, so how do we represent that in our code? Um, okay, so we have a class here. Okay. And inside this class, you want to have a vtable, right? Okay. So how about we create a struct vtable? Yeah. Sorry. And in here we say maybe we need another struct vtable entry, and that can either contain index t to function index or std string mname function index. Let's put that to invalid index, and then we need to say bool is pure virtual. Is pure virtual, but then it would, if it's pure virtual, it won't have a function index, but it would have a name. Yeah, we need a name then. Yeah, which won't be so easy. Mm-hmm. Mm-hmm. Pure virtual. Pure virtual. Mm-hmm. Okay. Okay, and then the vtable we say std vector vtable entry entries. All right. And then here on the class we have size. We put here vtable vtable. There we go. Mm-hmm. Okay. Okay, so the next question is I have about these two destructors. Why are there two? Why are there two? Let's look at these guys. So we have this one. Xfer. Let me save this address here. Okay. So we have this one, and we have this one. Now, unfortunately, the bytes are always inverted, so we need to swap this bullshit. 5, 5, 6, 6, 8, C, D, 8. Okay. There we go. Okay. Let's follow these. Okay, so this is a destructor. And down here, there's the other destructor. Why are there two? What's the difference between these? They look the same, don't they? Well, down here is some difference. Call 3 bytes and this operator delete. Why are there two destructors? They also have the same interface. What the hell? So we look at this code here. We have one virtual destructor here. Okay, so let me when we have two virtual, when we have two destructors in the vtable, then okay, then why do we have two destructors in the vtable? They are two functions which look similar. I don't know why it underlined this bullshit. do it like this. Okay. Yeah, I don't have an answer. I guess like let's ask ChatGPT. In vtables, I see two destructors. Why is that? Let me copy this stuff here. Clean it up a little bit. DD offset here. Let's see. The presence of two destructors enters in the vtable is a common pattern in C++. When virtual inheritance is used. Virtual inheritance? Or when a class has a virtual destructor. Yeah. This is due to the way C++ distinguishes between the non-deleting and the deleting destructors. Oh, okay. The deleting and non-deleting. In C++, when a class has a virtual destructor, the compiler generates two versions. Used when an object is destroyed without deallocation. Used when an object is destroyed and deallocated. How do we identify these entries? Both entries point to the same function address. Huh? That's not true. Both entries point to the same function address. Well, it's not the same. The first destructor entry is a non-deleting. The second is a deleting destructor. Okay. Okay. Offset to this. Non-deleting destructor, deleting destructor. Okay. 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 Let's take a note here. Vtable. Yeah, vtable has two destructors. Vtable has two destructors. ChatGPT explained to me there are two kinds of destructors, and it makes sense. Explained. Okay. Let's copy this information. vtable has two destructors. So we say one non-deleting destructor and two deleting destructor. Calls operator delete. And then we say when breeding in the vtable, we record only one vtable. Only one virtual destructor. A vtable has two destructors, non-deleting destructor, deleting destructor. Has two destructors generated by the compiler. Okay. Can we get rid of these red texts here? Yeah. Okay. Okay, I think we have a decent understanding now of the vtable. Now the question is, how hard will it be to pull it into our format? I think this will be the hardest part, getting the pure virtual names. Yeah. Okay. So we have a symbol name. I think we start similar to here. Similar to this bullshit here. Let me see. Type info. Oh. Right. So we have class name, class name. Here we probably delete vtable. How many characters are these? This is 6, 7, 8, 9, 10, 11. 11. Class name. Okay. Get content from virtual address. Why is there no function which just returns as a void pointer to an address? I don't know. Get content from virtual address. Okay. Let's see what other functions will take this argument here. Section. Aha. Okay, well, we can still use this one function there. It's kind of weird though. Get content. How about we rename this to let's rename it to memory. Mem. Okay. So mem. Okay, so the first bytes are always 0. Yeah. Guess we can just check that. Mem. We say uint32t mem. Oh, oops. There we go. Mem dot data equals 0. Put an assert here. Okay. And then we say how do we do it? We say function address point function address, and we say mem data plus 8, right? No? Value cannot be used. Guess we have to cast that. Let's cast it to data plus 2. Okay. And then we say for this function address is not 0, not null pointer. Hold on. Function address. I think that's not quite right. We need to say this and this and this. Okay. How about we say let's eliminate this here. For int I, why cannot not type int? I equals 2. plus plus I. And then we say so function address is that plus I. And then we say if function address is 0, then we break out of this loop. Otherwise, we keep on going. Yeah, then we do something with the function address. Let's put a void function address for now. Put a breakpoint here. I think this will work. Let's see. Let's put a breakpoint here. Okay. Let's see. Okay. Okay, so we have class name, vtable for overridable. Okay. Then we say memory. Okay. And the memory starts with 0, yeah. Then the first function address is this one. Okay, that one looks healthy. Yeah, and then we say, okay, this one is not hit. It's fine. Okay, let's see. Okay, so there were 2 functions and now there's a 0, so we break out and we are done. Okay, let's see if we ever get stuck in our loop or not, or if they all run through. Okay, always runs through. That's good. Okay, then we can say if function address equals this pure virtual, where are we? Here. If function address equals pure virtual, how about we not make it a enum class, just make it like so. I think it's okay to make it enum class. So we say here relocate symbol. We say static cast this. So if this equals that, then we say let's create a struct. I think we need to make some more change. We need to, this needs to be a second parse because we need to know all the functions already, right? Let me see. Hidden vtable xfer. Ah, hold on. Xfer. Xfer. Get options. Maybe we should pass these guys here before. Yeah. Get options. Get options. Okay, we get that. Okay, so vtable has vtable. So we have vtable entry. Vtable entry. Vtable entry. Okay, let's put this here. Vtable entry. Vtable entry. And then here we put vtable entry dot is pure virtual true, right? It also needs a default false. I put this here. This is pretty compact. This one not so much. Okay, so we know it's pure virtual here. That's good. And then down here we would say class name. We would have here find or create class by name. Let's take this one here. Okay. So I put this here, I mean class index. Let's just rename it class index. And then here we put m classes class index. And then we say vtable dot pushback. No, put vtable dot entries dot pushback std move vtable entry. Okay, there we go. Okay, let's put a breakpoint here. Now obviously we still need to do the vtable entry dot vtable dot function index to do and vtable entry dot function index. No, what was the other name? Right, to do. So we need to set these guys as well. Yeah. Okay, let's see if this works so far. Okay, we do get a hit here. That's good. And some pure virtual for symbol sound object. Let's try some other one. Body module. Body module. Let's see. Thyme body module. Don't have a body module. We have a body module interface. Let's try some other one. It's a lot here. It's a lot of pure virtuals. Okay, it's not ending here. Okay, update module. What about this one? Update module. There we go. Update module. It doesn't show any pure virtual here. Update module. Okay. Update module. Let's go type info for update module. There we go. And here we go in here. Oh. Well, that's not quite right. There we go. There we go. Update module. Oh, that's type info. We need vtable. Vtable for update module. There we go. Update module. Yeah, there is a pure virtual up here. Okay, and another one down here. Huh. Update module, type info. Vtable for update module. What is this down here? Okay. Update module. Oof. Okay, I'm a bit confused about this stuff here. Hmm. So there are non-virtual things. Guess we don't care about these. I'm not sure. Update module. Update module. It only has 5, 6, 7 virtual functions here. One, 2, 3, 4, 5, 6, 7. Get disabled types to process is down here. Okay, I'm really confused. Like, how do we work with this? Pooh. Get disabled types to process. Um, hmm. Behavior module. Update module interface. Behavior module. Yeah. I suspect that we can ignore this stuff here, but I'm not so sure. So this looks like compiler generated non-virtual functions to call the virtual ones or something. I think the interesting part is this one. Yeah, I'm a bit confused about those pure virtuals. Yeah. Because they don't show up here. Or do they? I don't see it. Well, maybe this pure virtual is just a pure virtual that's still from some parent class that we have not yet overridden. That could be. Yeah. Yeah. I see. Yeah, could be. Oof. We need a good strategy to pass those vtables. Right now, it's a bit complicated. Right now, it's a bit complicated. Yeah. I think it needs two-step process where we first gather all these functions and then we check which ones are being overridden and which are not. Yeah, maybe. Pure virtual. I think in our CPP types, vtable entry, we need to say bool is overridden, is override false. And if it is, only post, only add is override. Well, yeah, it's override. Essentially, all functions that are not part of the class, so behavior module is not strict. It is part of update module because of the inheritance, but oops, I didn't mean to do that. But we don't need to go. So it's implicitly added to the vtable. Update module. The question is, how do we communicate this in our own structure with ease? I want it to be easy to understand. So also our parsing with the passing to this also doesn't quite work now. Passing to 0 doesn't quite work here. -4. Offset to this, -4. Offset to this, -4. Polymodule. offset to this. F0, F0. Let me ask ChatGPT what that means. Can you break down the following vtable definition? Okay, type info for tint envelope, blah, blah, blah. Okay. Secondary vtable for secondary base or virtual inheritance. Offset to this, -4 for secondary base. What the hell? Offset to this, -4. Indicates this is a secondary vtable, likely for multiple inheritance or virtual inheritance. -4 means the vtable pointer is adjusted when casting from a derived class. RTTI pointer appears indicating belongs to the same class. Non-virtual chunks. These are adjusted function pointers used when tint envelope is accessed through a secondary base class. Secondary vtable exists indicating multiple inheritance or virtual inheritance. Likely inherits from another class. Uses multiple inheritance or virtual base classes. Offset to this, -4. Okay, my instinct tells me that we can probably ignore the secondary vtable. Secondary. Let me ask here, can we ignore secondary vtables, or are they useful for anything? The ones that contain non-virtual thunks. Offset to this -4 indicates this is a secondary vtable, likely for multiple inheritance or virtual inheritance. Let's adjust it. Does the offset to this value say anything about the class or base class sizes? Yes. Variable hints about class layout, base class, offsets, and inheritance structure. The first entry in the vtable. Offset adjustments needed. How it works. If the class is not using multiple inheritance and has a primary base, the offset is typically 0. If the class secondary base class, this offset is negative, meaning this pointer needs adjustment when casting to the base. This value correlates with base class sizes since it tells us where the base class starts within the derived class. Ah, Jesus Christ. Tin envelope is a primary base. Aha. Primary base. Offset to this 0. Aha. No adjustments needed when casting to tin envelope. Secondary vtable. Offset -4. I see. It's adjusted by -4 bytes. Okay. Line 20. Okay, so we have type info for tint envelope here. Okay, so offset. So this offset is 0. Okay. Okay. Okay, how about we create a new type here. Struct let's call it vtable header. So there's question is, how do we know how many entries are there in there? Don't really. We have this offset, then the pointer here to the type info, and then we have X amount of functions, but we don't know how many. That's a shame. There's an alignment of 20. It's alignment of 20. Vtable. How about we call it vtable info? And we call it uint 32t. We call it offset to this. This is offset for casting to this. And then we say type info, class type info. Const class type info let's call it offset to this. I would say you insert it to T. Type info. Okay, and then behind that there will be a uint32t function address 1. line 10. This needs to be adjusted by 4 bytes when casting from a derived class to this base. Base class for offset -4. There's some other base class that occupies the first 4 bytes in memory. Okay, so get content from future address. So we say size of vtable info, and we say vtable info mem.data auto vtable info. Okay. Then assert the first one. We expect offset to this equals 0. Then we say I equals 0. Say function address is vtable info dot function address I. If function address is 0, we break out, or if vtable function address I plus 1 equals if I plus 1 equals vtable info type info. It said this is end. Oops. Yeah, end of vtable. End of primary vtable, and this is break end of primary vtable, begin of secondary vtable. Right. Update module. I wonder if it can do anything useful with those offsets here. Not sure. They show what was inherited, I guess. Okay, I don't know what to do with this information. They show what was inherited. They show what was inherited. They show what was inherited. Huh? I don't get it. Isn't that what we get here already? Get body. Get body. Update module. Okay, how about we put a breakpoint here and say class name equals, what was it? Update module, right? Update module, yeah. Update module. Okay. Ah, shit. Oh shit. Okay. Okay. Then we need to put a different kind of breakpoint. If class name equals update module, then int a equals 0, and now we can put a breakpoint here. Good. Actually, hold on, we need to put it here. Okay, so we have class name update module. Good, so update module, and we already have a class index. So we go to classes, watch classes 0x11, update module, there we go, okay. It has two base classes. Which is number C and behavior module, and 12 update module interface. Update module interface. Okay, these are the direct ones, but there could be, there can be more in the chain, because these guys will also have base classes. Yeah. I'm still trying to understand if this gives us any useful information or if we can just ignore it. Right now I'm not seeing it. Behavior module, because these guys get body is here, everything is here. Non-virtual thunk. So basically this tells us that inside the update module class, we have an override here, or definition, right? It doesn't... Yeah. No. They show what was inherited, I guess. Okay, I have no idea how this is useful information for me. Let me read that one more time. Show what was inherited. Huh? Let me ask ChatGPT. Does the secondary vtable tell us anything about virtual functions that the primary vtable does not? Does a secondary vtable tell us anything about virtual functions that the primary vtable does not? Let me see. Yeah. Yes, secondary vtable provides key information about virtual inheritance and overridden functions and multiple inheritance that the primary vtable does not. A secondary vtable appears when a class uses multiple inheritance, uses virtual inheritance, overrides functions from a secondary base class. In your case, a secondary vtable includes non-virtual thunks, which indicate adjustments to this for method calls. Handles calls from objects of the derived type. Stores standard virtual functions. If the class is a virtual destructor, it appears here. If the class is not using virtual inheritance, this is the only vtable. Secondary vtable for secondary base or virtual base. Used when casting to a secondary base class. Stores adjusted function pointers to account for this pointer changes. Contains non-virtual thunk functions that corrected this pointer. These entries are missing in the primary vtable, meaning these methods are inherited from a secondary base class. Methods are inherited from a secondary base class. Oh. I see, okay. structure. Okay, well, I still don't understand if this is useful information for us. I mean, what is strange is that this guy here is the same as this one here. What does that tell us? That's weird. At least this one is different. Oh, it's really complicated. So the primary vtable. I have the feeling that we get everything we need from this guy. But we still need to look then into the base classes. Right. We do need to look into the base classes. Body module. So basically it has these overridden and these overridden. Yeah. I think I would need a break. No. Has been 2 hours 20. Yeah, let's take a break here. Maybe we go first just with the primary vtable, and then if we figure out, oh, we need some more information, then you can still look into this. But right now I don't see it. I don't know. Maybe here we have all we need. Maybe. Maybe. Maybe not. Okay. How about we stop the session here? Yeah.